Should I start? Oh, okay, it's 10:30. Boy, that's a bright light.
Sorry, Steve, I have to leave.
Okay. Okay. C'est la vie.
Yeah.
Good to see you again.
Yes, good to see you.
Okay, we'll just give it another minute and then we'll start. Hope everyone's doing well. Okay, I think we can start now. My name is Steve Wallach. I'm currently a guest scientist at Los Alamos and an advisor to the Barcelona Supercomputer Center. Today we have an extremely interesting presentation by Professor Luis Ceze, who is professor at the University of Washington. He will discuss machine language deployment and applications. With that, and then we'll have time for questions and questions after the fact. Luis?
All right. Thank you, Steve. Thank you all for coming. I know it's at the end of the conference, so I appreciate that you made it. So this feels very formal. This is the first bigger talk that I give since the pandemic, so it's great to see a lot of humans here. As Steve said, I'm a professor at the University of Washington, but a lot of my time lately has been spent my slides are not showing here yet. Yes, so most of my time is spent at OctoML, which you're going to hear more. It's actually very connected to the topic of the talk today. And with that, let me get started here. So I think it's fair to say this is rapid exploding, infrastructure ecosystem for AI and machine learning with, a large set of frameworks and models at the top. In fact, so this is a snapshot from Hugging Face just a month ago and had about 85,000 models just in the front page and several hundred being added on a weekly basis. And you have a Cambrian explosion of hardware backends where you want to run and map these models to. Okay? So far, ML models are being largely interpreted. What does that mean? It means that there's a graph that represents the model and there's an interpreter that looks at what the graph is representing and then calls low-level libraries that are typically written by hand, and they tend to be very use case or hardware specific. Okay? So what this means is that it can be painful and unproductive for users because every time you have a new model that's not supported, you have to go and call the system provider to go and implement that for you. And it can be very brittle because applications will break when the models change or the hardware changes. And so it's largely unsustainable for hardware vendors too because they have to keep up with the changes in the models and the framework. Okay? So there's a pretty windy, long, messy path between the models and the hardware where they run. Okay? So this is what we tried to attempt to solve at the University of Washington about 6 years ago or so. And the vision there with TVM, TVM stands for Tensor Virtual Machine. It's an infrastructure that automates the process of taking a machine learning model and turning it into hardware-specific, native, highly optimized code. Okay? So the way we see this is turning from interpreted way of looking at machine learning execution into a compiled way, like compiling models into native binaries. Go away from handwritten kernels and rely on using machine learning to generate very optimized low-level kernels. And instead of being framework and hardware dependent, be largely framework agnostic and hardware agnostic to offer portability and agility in enabling innovation in AI ML systems. So, and after TVM, there were several open compilers for machine learning, and it's been glad to see the action in that space. There's MLIR and MLIR dialects, OpenXLA, more recently, GLOW, and so on. Okay? So there's some consolidation going on. So let me make an analogy here that's possibly controversial. I would say that, machine learning so far has largely looked like the IBM in pre-80s. Okay, so IBM sold tightly coupled hardware and software. So if you want to use IBM database OS, you had to buy IBM hardware. If you want to use their hardware, you have to buy their software. Okay? So then in the mid-'80s or so, Microsoft decoupled the software from the box, with an operating system that supported multiple hardware. And then in the '90s, Linux open source operating systems. And I would argue that led to fast growth in both the hardware and the software industries. So the analogy here is the following, is that I would say that pre-2018 or so, ML was largely like that, like the mainframe industry in the 80s and before the 80s, with tightly coupled hardware and software. Okay? But now with these efforts in open machine learning compilers and system software, that decouples the models and the software infrastructure from the hardware they run, and that's already unlocking faster growth and innovation in AI ML. Okay? So, but why is this hard? So first, when you deploy machine learning model efficiently in hardware, you have to optimize the model at a higher level. Say you might need to fuse operators, a matrix multiplication with a convolution, for example. But then that's not enough. You have to carry this all the way down to the hardware and generate very efficient code for that hardware target. Okay, so you have to unify high-level optimizations with low-level code generation optimizations. But then you have hardware features like TensorOps, for example, that are very hard to use automatically. I know supercomputing has looked at vectorization for a long time, but now make that even harder with tensorization, right? Or making use of new memory hierarchies that are ever more complex. All of this, it has typically used by hand with people writing libraries, okay? So we need to find a way of using that automatically, and that's hard. And then the optimization space is gigantic. If you look at all the possibilities of how you reorder loops, choose data structure layouts, choose the right instructions at a low level, that's a gigantic space that needs to be searched efficiently, and you need automation from the ground up, okay? And then you have, on top of all of that, you have fast-changing hardware features and model requirements. So we need to have a stack that's highly extensible across the stack, from the model all the way down to the code generator. So here's what we built with Apache TVM. So Apache TVM supports all of the major frameworks at the top, TensorFlow, PyTorch, Keras, MXNet, and so on. And then he maps that all the way down to a large set of hardware targets by lowering it from the high-level framework. Let me see if this works. Okay, from the high-level framework here through a high-level data flow graph intermediate representation that's differentiable, so you can generate training versions of your code, to a lower level IR that's closer to the tensor operations, and then lowers this down through either native code generations via TVM that you're going to hear more about today, or existing libraries and compilers such that you get whatever is available that's the best way to deploy your model. Okay, so you don't have to rely on only one path from your model down. Okay? So the goal is really to enable access to high-performance machine learning to anyone, okay, and for any model. And it's built from the ground up with search in mind, with the point of view that optimizing machine learning models and contribution to the hardware requires search. It's not your typical compiler passes that we develop historically. Okay? So the goal here in the end is really to enable short time to deployment of models and make it easy to extend to new hardware targets and new machine learning models. So now, who should use TVM and why? So at the very top, we have the ML end user, and what they want here is to get their model to run as quickly as possible on the hardware of their choice, or have the system choose the hardware for them, okay? Because there's so many choices today. And then at the bottom, you have a hardware vendor or a system platform provider that wants to offer the best software stack to support the models that their users want. So TVM sits in the middle to enable hardware vendors and system providers to support the models that their customers care about and get the end users to get their models to run on the hardware that they want, from tiny devices all the way to large clusters. Okay? So let's go through some use cases of TVM to hope some of them will resonate with your needs. So the first one is just end-to-end model optimization. So what you want here is to get a model, say BERT, or a new computer vision model like YOLO V7, and you want to highly optimize this to the target hardware. Okay, so here's some. And the way that goes is we import the model, run both high-level data flow optimizations as well as code generations for that model, and then produce performance it's on the order of 2x all the way to 30x better than if you use the native deployment flow. And what you're showing here in this graph, by the way, is a mix of negative speedups all the way to 30x speedups with a mix of public models and private models. Okay, so public models, TVM doesn't do as well because a lot of those models are being optimized by hand. But the key thing here is that a lot of the models in deployment today and in production are customized for these. They tend to be private models, so they haven't received that much attention, and that's when you get the most benefit because there's more opportunities for optimizations that haven't been tended to by hand yet. Okay? All right, so that's using TVM for end-to-end deep learning optimizations. But now, how about classical ML? By that I really mean decision trees, like XGBoost style of models. What's interesting is that those are not deep learning models, so they're not based on dense linear algebra, okay? So what they're based on is a bunch of decision trees. There's this great work with Microsoft Research that converted decision trees into sparse tensor programs that you can go and use your regular flow of tensor-based optimizations to deploy these models. Okay, so some results show that it increases throughput 2 to 3x automatically in a broad set of GPUs, CPUs, and also future accelerators. So that's a way of unifying machine learning via tensor computing by converting decision trees into sparse tensor optimizations. Okay? So now, let's say that the other use case here is that you have a set of existing operator libraries and compilers. For example, say that you design new hardware and you have the best low-level programmers for your hardware, and you develop a set of basic operators that are implemented by hand, or you have your own code generator that you want to keep it private. So you can actually connect this to the TVM stack all the way up to the framework. Okay, so several case studies like ARM, Ethos NPU, or Amazon Inferentia, and several emerging ML hardware companies have been using TVM for that because you can go and plug in your existing library or existing compiler to the rest of the framework and enjoy the support for a broad set of models. Okay? So here's yet another use case that's closer to my heart. My background and my training is computer architecture. One of my favorite communities is the Astros Community that does a lot of hardware software code design. And say that what you have your own new deep learning accelerator or machine learning accelerator that you want to connect to the rest of the software stack and have software support from day zero. Okay? So what you need to do is you need to support rapid hardware software code design with a software stack in the loop, not relying on tiny little micro benchmarks that by the time you're done, they're not representative of what the workloads actually do. So to illustrate that, we open source, I think one of the very first open source machine learning accelerators that's also in the Apache Software Foundation project that showed a TPU-like design that's fully open, that's connected to TVM, and we show with TVM the ability to do very rapid hardware-software feedback because you could change the hardware, and as long as you kept the same interface, you had the software stack on top, and you could try new workloads on your hardware design. And you can do that by plugging in your FPGA emulator, for example, or FPGA implementation, or you can even plug in simulators, based on Verilator, for example, so you can actually try the software stack on hardware under development, okay? So here's yet another use case. So this use case here was about bringing new hardware into the picture, okay, to do hardware software code design. Now, another use case is if you have a whole new model. For example, you have stable diffusion, okay? So there's an operator there that is not supported by any of the existing software stack, including the most mature ones, for example, on NVIDIA hardware, okay? So we want to enable users to write new kernels, new low-level operators in a very fast way and enjoy the automation that decouples from the small details of the hardware. You want to enable auto-tuning, the ability to search for the best implementation while you're writing these operators, okay? So, that's why we essentially create an interface called TVM script that allows programmers to express these low-level operators in a way that they can enjoy all the automation that we offer. Okay, so here's some examples. Early on, this is a couple of years ago, we did with Hugging Face support for prune BERT on AMD GPUs and show over 2x compared to a naive to the existing implementation. Same thing with NVIDIA GPUs as well. We did this for supporting sparse kernels and compared well with cuBLAS and cuSparse. Support for very unique data types, for example, single-bit end-to-end acceleration on CPUs, or more recently, support for new models like stable diffusion. Okay, so by writing, very quickly enabling programmers to write the operators at a low level. So now, here's the final one, and which is in the opposite spectrum of supercomputing here. This one work that's getting quite a bit of attention. We call this micro TVM, that enables one to get a machine learning model and compile it down to a bare metal executable. Does not depend on operating system libraries or anything. Like you can actually flash the model straight into a small device based on ARM, MIPS, RISC-V, and so on. Okay? So we had a recent ML-Perf tiny submission using TVM that illustrates how well that works. And I'll say that tiny ML is a huge opportunity because there's a lot of really interesting use cases, and people are coming up with more and more really exciting ones, from health to environmental sensing and so on. Okay, so now one thing I'm being very proud of is to see TVM grow in 6 short years into like an open standard for ML's system software stack. It's being used in very large-scale production, in large-scale smart speaker systems like Alexa. Facebook has used it, Microsoft, and a lot of hardware vendors like Qualcomm, ARM, AMD, Xilinx, and several emerging hardware vendors. The community today has over 700 active contributors from industry and academia, and it's been in large-scale production for about 4 years or so, and we estimate that it runs in over 1 billion devices today. So it's great to see the impact. And I want to say here, huge thank you to the open source community, because reflecting back, I don't think it would have been possible to get where it is today in supporting this large cross-product of frameworks, models, and hardware without an open source community underneath it. Okay, so open source communities really makes this diversity manageable and ensures future-proofness, because there's always, even if the key the folks that started are not focused on it anymore, there's still continuity in focusing in entities investing in developing the software stack. Okay, so make it future-proof. So now to zoom out, you can look it online to look at what resonates with you, but a summary of the technology advantage of using TVM is, broad framework support, historical ones and new ones. There's ML-driven code auto-tuning that you're going to hear more about now. We support different hardware types. In fact, it's very highly extensible. So we support deep quantization and specializing your code to different data types. We support split graph execution, so you can have a machine learning model to run a hardware target that has CPUs, GPUs, NPUs, or reconfigurable units, and you can actually break down your model to run where it runs best automatically. We support bare metal compilation, just told you about for IoT, but also the same thing can be used to compile a machine learning model to run on WebAssembly or Web GPU, to run it in a browser in a highly optimized way. And we have support for sparse tensors too, which is very useful for natural language processing models, and large language models are being seen so far. And finally, it allows you, with the TVM stack, you don't have to rely solely on the TVM platform model to code generation. You can use existing libraries and code generators and mix and match for what works best in a given scenario. So this framework allows you to invoke the right pieces at the right time. Okay? But now let's dive deeper. And as an exercise, I just did this last night. I typed it into DALL-E 2, diving deeper into a sea of code. And what's funny, if you look closer, this looks like it tried to get binary code intermingled with what looks like code. But when you look closer, the symbols don't mean anything. So this is what AI-generated images look like today. It's kind of amazing, but when you look at the details, it can be even funny what it's doing there. Okay, so. All right, so let's dive deeper. So how does the optimization using machine learning here work? So here's a high-level diagram of how this works. Okay, so let me get my pointer here. So you start with an initial program, then you specify a search space here that we're going to talk about more in a second. And then you generate code, you run it on the hardware, you measure how long it takes to run that piece of code, you collect data. And then by doing enough of these variants, you can build a statistical cost model of how your hardware behaves. Once you have that, you can try a large number of variants using just this predictive model to determine what it's worth to do the full loop again. Because this full loop here could take a second. And if you have 10 billion of these options, it's going to take too long for you to try them all. So you have to run it a few times, build a model, and then predict whether or not you should do more experiments. Okay? So how do we build these models? Well, we explored several ways. There could be a whole nother talk here. Several ways in extracting abstract representations from your program, your tensor program representation here, and using in machine learning models like, we use primarily decision trees in this case, and some deep learning as well, such that we balance the complexity of the model itself. It has to be cheap enough to call, right, to put it in a tight loop for optimization, but it has to be rich enough to represent complex behaviors. So we arrived at one that extracts, the shape of the loops, how the induction variables look like, what is the shape of the data structures that you have choice, and so on. So you can extract this representation from your code in a way that's largely independent of what you're trying to do. Okay, because if it's too dependent on that, you can't generalize it. So then the way this works is we extract this hierarchical optimization space from the code automatically, and then we can start from an existing repository of this cost model, so you don't have to start from scratch every time, which can take too long, okay? So this thing, basically, the more you use it, the better it gets, and what's cool is that you can change the task, the type of code you're gonna apply it to, or you can change the hardware, and you can learn very quickly how to adapt to that new program-hardware pair, okay? So here's some results that we had here. So the dashed line here is the baseline, in this case on NVIDIA hardware, so using cuDNN, so highly optimized code written by folks that really understand the hardware. If in the blue line shows just, the dashed red line is just black box auto-tuning, okay? So that's when you just blindly try multiple variants. Then you can run a large number of variants and you never get to human level accuracy, okay? Because you're trying a lot of stuff that's not worth it. The blue line is using this ability to learn and predict when you should try new variants. And then very quickly, in about 100 tries or so, you start doing better than humans. But then in the red line, that's when you inherit, you do transfer learning from similar enough programs on similar enough hardware, and start from that. And just with a few tries, you can learn a very effective code, a very effective model to predict how the hardware and the code behaves, and you can use that to tune. That means very, very quickly you arrive at much better implementation. And the y-axis here, by the way, is just speed up over the human-tuned version. Okay? So that's the gist of how these machine learning-based optimizations work in TVM. All right. So now let's dive a little bit deeper now. So a lot of this code optimizations is about really scheduling, how you schedule the execution of your code on the hardware substrate. And TVM started early on, inspired by Halide. Really love the work on Halide, if you probably heard of it. So Halide proposed this idea, Jonathan Reagan Kelly and his colleagues proposed this idea of representing a piece of code as in two ways. One is a functional definition. For example, you're doing a matrix multiplication. And the other one is a sketch of how you should execute, the schedule of how you should execute that to make the most out of the hardware. These are things like how do you do tiling, in what order you execute the loops, and so on. Okay? So in this example here, we're doing a simple linear algebra operation on the left here, and then on the right side, we're saying how we're going to split and do tiling. Okay? And then you write those two by hand. But I would argue that only the left side should be written by the programmer. The right side should be done automatically. And that's how TVM evolved. The first version of tuning TVM was published in NeurIPS about 4 or 5 years ago. Essentially, instead of writing a schedule that determines exactly how the code should run, you provide a template, and then the system searches for the right parameters for your schedule. Okay? So the pros there is that you can inject some domain knowledge, and you enjoy the automation of filling in the blanks. But the con is that you have to write a template, and that takes work. Okay? So, and also difficult to scale across operators and target platforms. Now, the second version of that a couple of years later was AutoScheduler, where with a set of high-level rules, you can automatically extract how the shape of the schedule should look like, and then do auto-tuning on top of that. So it's further automated. Okay? So the pro is that you don't have any direct engineering effort required, you just have to write these rules. But the cons is that you have to extend the rule system depending on significant changes on the code or significant changes on the hardware. And it does not really work well for cases where you want to use new, more exotic hardware features. That's where I arrived at the latest version, MetaSchedule, which is going to be published in NeurIPS later this year. It's already in production as well. And the way that works is you provide the function definition of what you want to compute and a functional description of the hardware. That's all you do. And then you can also provide a manual set of templates in case you want to inject more domain-specific knowledge. But the idea with MetaSchedule, you can do as little as just describing what the hardware does, or as much as providing a template. But then whatever you provide is actually going to generate a gigantic search space and use a large number of heuristics to navigate that efficiently, okay? So, and then the pro here is that you get the best of all these approaches that allows you to provide the domain knowledge that you have about what you want to compute. Maybe you don't have much, or you know it's a hardware, that's fine too, except it's going to take longer to find a good implementation. Okay? So it has better debuggability as well, because you only have to debug the functional definition, the functional expression, and not the template itself. Okay? And then we've shown consistently that this leads to all the way 1.5 to 2x better performance than highly optimized hand-tuned version of that, even in leading implementations by major hardware providers on new code. Okay? So that's MetaScheduler. So, and then with that, by the way, so it's interesting to see that this has been working really well on the latest machine learning models and latest hardware, and very, very quickly supporting new models on new hardware. We're talking about a matter of weeks, sometimes days, you have really good implementations, as opposed to what would normally take months or maybe half a year or so. Okay? So now what's next for TVM? And here's another DALI one. So this one now is robot looking ahead into the future in the style of Alexander Calder, which is one of my favorite artists here. And it actually did a pretty good job, representing a robot trying to look into the future. But to talk about that, let me tell you a little bit of what we learned. So when building TVM, we had 3 personas in mind, okay? So we had the ML and user engineers. These are folks who want to deploy machine learning models. The second persona is the machine learning infrastructure engineer. These are folks that are writing, the system software to support the framework and the end users. And the third persona is ML hardware engineer, folks that are designing new hardware and designing the low-level, microkernels to support all of that. We made that very modular, so you could evolve those independently, and that was good because it led to very functional implementations. But one thing that we noticed is that that was not enough, because changing that and evolving that took work, because now you might have the ML hardware engineer waiting for the ML infra engineer, and that's also waiting on the ML end user. They're all writing what they need in different abstractions. So, and doing that actually hurt velocity, because you couldn't have a single abstraction and allow this to evolve in a much faster way. So this is why there's this effort called TVM Unity that should land by the end of the year, or by the latest by next TVM conference next year. TVM Con this year is going to happen this time is going to happen in March of next year. And we wanted to create a single abstraction that's Python-based, that allows the ML end user engineers, the ML infra engineers, and the ML hardware and system software engineers to use the same abstraction, okay? So now you can express your computational graphs using a language that we call Relax, at the same time that you specify how you should represent your tensor programs to do better optimizations or enable new kind of operators. You want to make the most out of existing libraries and compilers via FFI, foreign function interfaces. And you want to be able to automatically use hardware primitives. So we've demonstrated recently the ability to use, for example, new CPU instructions for matrix multiplication for tensor operations in a very, very easy way that even the high-level model engineer can actually use by specifying what is it they want to compute, and then relying on a very high-level description of what the hardware does, okay? So unifying all of that across all personas really increased velocity, and we're already seeing the impact of that. Okay, so now let me zoom out and talk a little bit about OctoML and why I got super excited about where TVM was going and all of the traction that he got. And we thought there was an opportunity to extend that to a much broader set of users by creating a company around it in a commercial setting, and a product that's even easier to use than what TVM is, okay? So, and this came from the observation that if you don't build an application out of the machine learning model, that is the innovation there, it's just a cool demo. Okay, so there's a lot of cool demos out there, but if you don't embed that into an actual application, you just don't have the impact that it could have had, okay? But this takes a lot of work for folks that actually build end-user applications today. It's a really long road from model to the actual intelligent application, okay? You have to have specialized engineering efforts that understands machine learning, software engineering, and even computer architecture in some cases to actually produce a working piece of software. Okay? But once you get there, it's typically very hardware dependent. It depends on specific CPU or GPU or combination of those. And then once you do deploy it in the cloud, you have massive infrastructure costs because they use a lot of computation. Okay? And so we wanted to change that. And what we did with OctoML is subtract away all the complexity of getting a machine learning model into an application with a fully automated infrastructure that uses TVM and other components of the system software stack to produce a package that's high performance, it's portable across different hardware targets, CPUs, GPUs, and between CPUs and GPUs, and it's production ready to be deployed in cloud settings or in the edge. And this automation, by the way, it goes beyond code generation. It's not generating just the code for the target hardware. It's actually combining all the dependencies, combining all of the interfaces that you need to be able to integrate it with existing application frameworks. So that's what it's all done in a SaaS way, so you don't have to install anything. Just go to a service that is accessible either via a high-level web interface that you get a lot of data about how the model behaves, as well as an API to integrate this into your CI/CD infrastructure. Okay? And then what it navigates through is navigates through the existing libraries, say, AMD ROCm or Intel OpenVINO or NVIDIA cuDNN and so on, and then maps this to all of the different hardware. We support all the major clouds, AWS, Azure, and GCP as well. Okay? It searches not just the code, but also searches, hey, data layouts, tensor layouts, what kind of optimizations you're going to do in it, and also what hardware you should run it on. It can recommend to you which hardware you should run, and it produces like even the cost and how much it's going to cost for you to run this at scale. And for every single data point that it produces that you can choose from, it's actually a functioning, ready to deploy piece of code. Okay? So you can go online and see, but OctoML has been doing super well. We're about 130 people now. We have real customers, and it's great to see the impact that academic research can lead to industry. I'm just going to finish with some thoughts here, if you don't mind, Steve. So the final one is I started in HPC. I came to the US 20-something years ago, worked at IBM Research on the Blue Gene project. That's how I got started. And I did a lot of high-performance linear algebra then. And when I see today what's going on in machine learning, it's all about doing very, very fast high-performance linear algebra in a much more diverse setting. I would say that the hardware and software infrastructure for AI/ML is extremely messy, and that's a major opportunity. And a lot of that can be addressed using AI/ML itself. Okay, so that's why I like using this Astros picture here of a hand drawing itself, because you can see of AI/ML being used to design better AI/ML systems to run AI/ML better and close the loop. Okay, so open source communities is really important to make all of this work, because that's the best way to deal with diversity and future-proofness. It does have its governance challenges, but I think it's worth it in the end, because making it independent helps with adoption, even at the cost of some velocity. And then I would say that seeing this going from research project to open source infrastructure to a company has been eye-opening. Now I fully understand what one says, that most of the effort goes into the last 10% of making something actually work, and everything breaks at scale. So with that, I'd love to take leave 10 minutes for questions here. So.
Thank you. I learned a lot. That's I find it always interesting how HPC is moving from solving partial differential equations or the weather to machine learning and open source. And it's how open source, FPGAs, RISC-V, and everything else is actually helping this, where 20 years ago you didn't have
that, right?
These fundamentals. So that was really good. I learned a lot. Okay, we have time for some questions.
Yeah, questions.
Thank you for the talk, Luis. First of all, I completely agree that the space of ML software infrastructure is very messy and fragmented.
Yeah.
So going back to the first part of your presentation, what are your thoughts on the need for standardization in that space, and whether that's even feasible in a certain timeline?
Yeah, it's a great question. So of course, it's standard. There's no way to argue against making something standard to allow it to more folks to participate and you need that to be able to evolve the system software stack and the hardware stack in a way that decouples it from from the rest of the other implementations, right? There have been several attempts, right? You've seen Onyx. Onyx has its ups and downs, and now I think it's become more as a way of representing, the high-level model. I like what's going on with the Ceze effort of trying to come up with a set of, tensor operations that you want to support as standard. And this is all, I think, trending in the right direction. It all depends, I think, in the ability to convey this to the folks creating the machine learning models. Because if you don't make these standards accessible and understandable to folks that are actually doing fast-paced machine learning evolution, everything's going to break. Because they're always going to come, you're not going to support their use cases. So my main thought there, I'm just babbling here, but the basic thought here is, I love standards, of course. We're betting that some of them is going to work. I don't think it's going to be one is going to work for everyone, but I think the ones that have a higher chance of success are the ones that are going to be tightly coupled with how folks actually think about creating new machine learning models.
Yeah, thanks. Just a follow-up. Do you think would it also be important for a potentially new standard to provide migrations from the existing standard, the existing tool chain to the next one?
Yeah, absolutely. And by the way, we do that a lot. So in fact, we have native, like in our commercial SaaS products, or I don't mean to make, a shameless plug here. A lot of what we do that has a lot of value is help folks port old models in TensorFlow to new representations that can actually use new software stacks. And creating translators between those is a huge opportunity to keep this huge business opportunity, but also an opportunity to keep evolution fast, right? So, yeah.
Hello. So I think that when it comes to developing code, none of us trust ourselves to begin with, and most code ends up taking 70% of the time debugging what we figured would work the first time.
Right.
And I think one fear I'd have using some of the process you mentioned, defining my functions and defining this schedule, and then letting a machine handle it, is that I would have no idea how to debug it if the machine failed. What kind of guarantees, how can I be reassured that if there's a problem, I can just focus on fixing my own thing instead of sitting there questioning the machine?
That's a great question. This is why we evolved the first version, just doing blind auto tuning, just very hard to debug because tends to be very hard to debug because the implementation that actually breaks can be fairly removed from the high-level specification, right? But now the way we evolved is by creating much more systematic ways of extracting the templates from a native implementation, allows you to trace back. When something doesn't work, you can much more easily map this back to what part of your high-level specification the problem relates to. And it also allows you to determine whether the bug came from a high-level specification error or a translation error. And then you can actually automatically narrow down to a much smaller set of things that humans can reason about. But I'm with you 100%. Like if we just do this blindly, we could lead to very, very hard to debug scenarios that might defeat the purpose of doing automation in the first place.
Yeah, I'm guessing if you see a translation error, the next thing you can do is go file an issue on GitHub or Jira.
What is that?
Oh, and I figure that if it's a translation error, the next thing you can do is file an issue on GitHub, Jira, etc.
And right, yeah, you can find it. Yes, if it's in the specification, or if it's a translation error, I think there's a lot of opportunities to do this in an automated fashion to narrow down to a very descriptive example that's what you go and file as a bug for a human to look at.
Okay,
right? So,
thank you.
thank you. Thanks. Great question.
We have any other questions? Gentlemen.
Hi, and wonderful work. And so I have one question about fundability and accessibility of frameworks like yours. Because I think a lot of people are new to this field. There are just so many models, data sets, frameworks. How can them become kind of easily fundable by people to solve particular problems?
Yeah, I mean, thanks for asking that. And again, I have to say this, that we cannot solve that with just TVM because I don't think it's that sufficient. So that's the whole point of actually abstracting away all of the details of turning a machine learning model into the very best package that you can deploy. And I don't think today, at least, you cannot rely on a single path, on a single set of libraries and compilers to do that. You have to search automatically for what's the best option. And that's what we did in the OctoML platform, is exactly that problem. We want to not have a human have to worry about how to map a high-level model to the very best way of producing an executable for that model, taking into account not just open source alternatives like TVM or like MLIR dialects, but also some hardware native options like cuDNN, TensorRT, and Cutlass for NVIDIA, or ROCm or AMD. We want to search what's the best one. And then put an outer loop on top of that, even to search for different hardware automatically, so you know which hardware you should run it on. It's going to have the best cost performance choice, right? So I'm with you that today, it's a huge mess, and the way we're solving that is by letting computers do that for us, by creating a very, very large automation loop around that process, right? So.
And one missing piece, maybe the data sets. Quite often, people want to find the right data sets for driving some kind of workflow. How do you solve that?
Yeah, it's a good question. So the way we look at machine learning model optimization compilation is actually, and I think should be agnostic from the input data. We should treat that as compiler transformations that does not change the model property, so you should be talking to the data set. Because if you include the data set as well, then the problem becomes a lot harder. But I do think you can actually separate these two concerns. You can validate your model with the data that you care about, and then everything else, should not violate your assumptions when you validated the model, right? So.
Thank you.
Of course, yeah.
Do we have any other questions? I'd like to ask a question, unless anyone, you have I'm sorry.
Hi, thank you for the very nice talk.
Of course,
I'm just curious, you showed this graph in which you said that we could find out what is the optimal model and what is the cost of a model for a given task. Have you retroactively looked at some of the, say, submissions that were successful at big conference to see the cost or how bad they're doing in terms of the model they chose? Some of post-mortem analysis?
Yeah, so that's super interesting. If I understood the question correctly, you said, have we looked at popular models that get published in conferences to see how they do? We do have an internal set of, relatively large set of models that includes everything from language models, computer vision models, to life sciences related models like protein folding and so on, and find really good implementations of them for folks to go and deploy. And in many, many cases, we actually find really good implementations of the model, but not a better version of the model, just a better way of running that model than the paper had in the first place. And it's not just to say, see, we do it better. No, it's just to show that we want humans to worry about how to build the best model possible for the tasks that they want to solve, and not have to worry about system details. Like, for me, it's heartbreaking to see brilliant humans that should use their cognitive capacity to build better models, worrying about, hey, for me to be able to do this thing in my model here in protein food, I have to worry about this small detail in the GPU. In my view, this doesn't make any sense, because I want that human brain that knows how to reason about the model to focus only on the model and let computers do the rest.
Yeah,
right,
I understand. So that's what I was asking also, in the sense that now that you managed to optimize this, it would be interesting to understand how much we could save in terms of money, energy, compute cost for models that were running arguably many times also for hyperparameter tuning and things like that?
Yeah, absolutely. So in fact, we partner with several. Let me just show you one thing that we have here. So for this plot here that you can see, like you can see the costs here, how much we can save. So we run on a bunch of models that are popular, essentially to show users the benefit of using the platform, right? And now there's actually a way even for you to translate from dollars to carbon emission equivalents, for example,
yes.
And show that, yeah, folks should use technology like this to actually save on costs and also save on carbon emissions as well. So great suggestion. Thank you.
Thank you.
Excellent. Anyone else? I'd like to ask a question.
Yeah.
3 years from now, which AI application, ML, will make, let's say, the front page of the New York Times and Washington Post as, this solves something that no one ever thought could be solved, or will change the way we do things?
Yeah, so this is totally, I think the question is, what I think is going to get the most visibility as a machine learning solving a problem that no one has solved before? I would like to believe that it's going to be in life sciences, in designing therapies, or like a fully automatically designed therapy. people are getting close to it, like what's going on with, rational protein design using machine learning. Folks like David Baker in the Institute of Protein Design, for example, they have methodologies to design, fully synthetic proteins. And in fact, the first vaccine was approved to use in Korea, a COVID vaccine, fully designed. You probably have seen that. They want to still had human involved.
Right.
Human involvement. But I would say that we're not too far from actually having from specification of what is the shape that you want to act as a vaccine to generate this antibody response, and do like a fully automated design and generation of the DNA sequence for you to go, do the process of extracting the protein, right? So I think that's going to be the one that's going to catch the most attention.
Oh,
The one that I think
when
that's
that happens, whoever does it will probably get the Nobel Prize.
What is that?
If that happens, whoever does that will probably get the Nobel Prize.
I will not be surprised that a Nobel Prize. I will not be surprised that a Nobel Prize will be given to protein designers. So.
Very good. Well, thank you. I appreciate that.
Cool.
Okay, are we done?
Any more questions?
Any more questions? Well, thank you all for.
All right.
Thank you very much.
Thank you.